please welcome Daniel and Tanya for their talk about high-assurance crypto software.
Thank you. So why is high-assurance crypto software a thing? Why do we worry about the correctness of software or the quality of software? So just some recent news results about, well, crypto getting broken so badly that the private keys leak. These are just reports from October and November. And this one nicely adds a pun saying timing is everything. So these were some timing attacks which completely broke elliptic curve-based cryptography so badly that the private keys came out. Timing attacks are not a new thing. So back in the days when you logging into a server and that is looking at your password, it might be doing a character-by-character check. So for instance, you were starting by, well, let's find out what the first character is. So you're sending AAA, well, BBB, CCC. Now, of course, none of them will actually work. This would be very surprising if this was the right password. But you do observe the time it takes to say this password is wrong. And then you notice that CCC takes a little bit longer to fail. Yay, CCC. Then you're trying CAA, CBB, and so on, still fails, and they all take about the same time to fail until you're getting to COO. And then you're trying again for the third character, and so on, and so on, and so on. So eventually you get the password. And this was actually a thing. This was 1974, the Tenix system. So it was an operating system where you, well, back in 1974, before most of us were born here, you could log in and it would be just doing this character-by-character checking. So timing attacks to break cryptography or break security have been known for a long time. But of course, things are getting more subtle when you go into cryptography rather than just character-by-character comparisons. So for instance, if you're implementing your favorite crypto system, be it Diffie-Hellman Infinite Fields or be it RSA, then each time you have to compute an exponentiation. And then you go back to your Crypto 101 lectures and don't compute C times C times D times, but you remember that there was a square and multiply algorithm which tells you, okay, you're looking at the bits of the exponent. So here, I'm going for the representation of D in bits. I'm looking at the length in bits, and then I start by initializing, so you can run this just Sage code. You're initializing your finally gonna be the message in RSA, and then for each step you're doing a squaring, and if the bit is set, you're doing a multiplication. And this runs from, well, the first bit we've dealt with already, so the second highest bit, till all the way to the 0. Which, okay, in Sage, this is, well, like in Python, so this is the range is not included. And then you output the ciphertext, the plain text. Now there's some problems with this. So if you're an attacker and you know that your user is using this to compute an RSA decryption, then you observe that this loop length gives you some information on D, namely the length of D in bits. This L was defined as, well, how many bits does D have? And then some Ds, well, this D looks rather short. This D is much shorter than N. It's much shorter than phi of N. So this would be an unusual D, and so it would leak that it's a little bit shorter. Also, here we have a branch. I go, if this bit is 1 and not, then, well, I'll just continue. So depending on the level of fine-grained access, somebody could even see whether I'm going for a multiplication or just moving on to the next squaring. In the worst case, somebody could read out the pattern of zeros and ones by just knowing whether I enter this branch here or not. Now, if you're a remote attacker, you only see the overall time. Now, I have a picture from something similar. It's not an exponentiation for RSA, it's an elliptic curve scalar multiplication. This is from a recent paper from TPM Fail. And they observe how long it takes to compute, well, the equivalent on elliptic curves is scalar multiplication, so you do double and add instead of square and multiply. And you can nicely see that the bulk of the computation, well, for most exponents / scalars, it takes this long. And if you have some leading 0 bits, it's much faster to still somewhat faster. Now, there is some variability. And it could be faster because your D is very sparse. It could be just 1 and a whole bunch of zeros and then another 1. That would also be as fast as something which is a few bits shorter, but then more dense. So that you don't know exactly whether it was short and therefore fast, or whether it was sparse, so few multiplications and therefore fast. But if it's a lot faster, it's probably both. The top bits are missing, and therefore you don't have multiplications there. So if you're very fast, you have a good guess that this thing was actually short. And so there's a strong dependency on the length. There is also a dependency on the density. Now, typically, your implementation will actually not be doing it. I was surprised that this paper found an example where you're really going bit by bit, because of most of the time, our time is very precious, and so we want to speed up things. So if you're taking your favorite number, like 1419, also known as 3663, and you write this in binary, and then you want to do your multiplication, well, your scalar multiplication starting from the top bit all the way down, similar to the RSA loop, but you want to save on the number of multiplications/squarings, then you would be grabbing 2 bits at once. You pre-compute a few values. You pre-compute your c squared, and c cubed. And then to compute this exponentiation, you're kind of doing 2 squarings at once. So you're doing 2 of these positions at once. The first one you can skip because it's both zeros. The next one, the 1, 1, gives you a cube. So we're starting with c cubed, which we nicely enough have pre-computed. Now, we're moving on by 2 bits. So instead of squaring once, we square twice, so that's why the 4th come in here. Next position is 1, next position is 2, so we see a multiplication by c, computing to 4th power by c squared. So everything is like in the previous loop, except for we're doing 2 bits at a time. And so instead of saying, oh, if the next bit is set, we do a multiplication, we look at the value of the next bit, and then select from c squared, c cubed, or no multiplication. And this definitely reduces the number of multiplications. This would have normally taken 7 multiplications, and this way we only take 4. It doesn't change the number of squarings. Now, this will smoothen out the effects of having a sparse integer because, well, as long as there's a single 1 in the window, we call this thing a window here, then it will cost a multiplication, whereas normally it would be 1 multiplication and no multiplication here. So when you look at the traces from this, then you get much more accentuated boxes, whether something is 0 at the beginning or not, because most of the other steps, in particular for larger windows, this seems to be taking 4 bits at once. So for the larger windows, most of the time, I mean, if you have 4 bits, then there are 15 cases out of 16 where you have to do multiplication, and only 1 out of those 16 where you don't need a multiplication. So it accentuates the length issue, and kind of, you have no idea whether the bits were set or not, I mean, how many bits were set. Now, how much does these few bits do? Of course, you don't want to leak your secret RSA exponent, you don't want to leak your Diffie-Hellman, but it's not too bad there. It's really, you would need a lot of knowledge, you need to have either extremely short or extremely sparse to actually break something with this. It's kind of worse if you're having RSA with Chinese remainder theorem decryption, because then you can do some combination tricks. So there's something we gave a few years ago, how you can combine information if you know a few bits of D modulo P and of D modulo Q, and then you combine these, so then you learn more. When it really goes bad is if you're doing signatures, DSA signatures, or ECDSA signatures. So these are systems which are extremely fragile, and it's a strange thing that by just looking at the scalar multiplication for a number which you will use only one single time, so your signature generation starts with, you pick a random number, you do an exponentiation or scalar multiplication, and then you do something else with this number. These one-time numbers, these one-time exponents, if they are somewhat biased, for instance, if you know that the top 4 bits or top 8 bits are always 0, you're getting the secret key. So it is a very, very strange system that this is possible, and this was exploited in the 2 papers from which I showed you the news coverage. So there was a TPM fail this November by Daniel Mogimi, Berg Sunna, Thomas Eisenbart, Nadia Henninger, who showed that doing this to typical TPM implementations of TPM cryptography, so you have your TPM in your computer in charge of doing the signatures, say for a VPN connection, then they could get the keys out of the TPM remotely. There was another paper called Minerva Attack. I haven't seen the paper yet, but they have a very nice and informative webpage, Jan Ganka, Peter Svender, and Vladimir Stetlach, where they're doing the same for smart cards, which were actually certified. So this is really bad attack, and it's something where all these implementations, both the TPM and the smart cards for the signatures, should have been tested for this before. But apparently people didn't test or didn't realize that this small bias has such a huge effect. There are more attacks, so this is just the basic, you see the overall timing, but this already broke lots of libraries, smart cards, and TPMs. If you're getting more detailed information, if you are on the same processor, like you're running a hyper-threading attack or cache timing attack, then you might even be able to figure out when you're doing the lookup for the pre-computed values, where this lookup went. So you're kind of booby-trapping the table where you're going to look up something, and then depending whether the processor fetches this entry, which is in cache, or that entry, which is not in cache, you're learning actually something about the exponent, and you can even recover the exponent from these things. Now, this should be a constructive talk. We said this is like 80% constructive, so let's jump in. How would you fix this? So one thing is, for all our crypto implementation, we actually know kind of an upper bound. This is not an arbitrary exponentiation, it's an RSA decryption. We know that our RSA keys, well, we know a bound on the end. People pick 2048 or 4096-bit keys, so we have a good upper bound on how long this D will be. So why don't we just use that? So we're making this loop length independent of what D actually is, but just saying, well, we take the number of bits in N rather than D. All right, so the problem then is, before that we started to initialize our message with the ciphertext, and then we kept squaring and multiplying. But there's an easy way out. We just initialize at 1, and well, if you square 1, it stays 1, until, well, you have reached the bits that are actually occupied by D. So when we expand our D, we're padding to the full length, and we're initializing at 1, so we have a fixed length loop, and this one takes care of not modifying our values. And then we do the normal thing, we square and we conditionally multiply. Except for we don't want to have this if-else. I mentioned cache timing attacks, and in general, well, you might be leaking, well, you're definitely leaking how many bits there are, and you might be leaking more depending on how different your multiplication looks from the squaring. And so what we typically then do is we give up on a bit of performance, we do a multiplication for every bit, not just if the bit is 0, and then we conditionally select which of the two to take. The one which we just computed, the H here, that is with multiplication, or the one without multiplication. And we don't want an if and else there, because an attacker could observe the branch, could see whether we're going or we're not going. And so we do this whole thing by arithmetic. Well, okay, let's briefly run through this. If the bit is 0, then I have 1 minus 0 times m, so I'm getting m, great. And then if this bit is 0, I'm taking 0 times h. So for the 0 bit, I'm computing m, which is what I wanted. And now for the 1 bit, I should be grabbing h. And yeah, of course, if I have 1 minus 1, this is 0 times m plus 1 times h. So this small modification to the code comes at a bit of a cost. So it's as slow as the worst case, both in the length. So our loop has gotten longer. We're doing more multiplications, more squarings, and we're doing a squaring and a multiplication for each bit, which otherwise would have just been the worst case. Now, I've been saying elliptic curves, and I've been saying Diffie-Hellman RSA, so if you're doing Diffie-Hellman fine field, you can do exactly the same thing. You can initialize at 1, and then multiply by your generator, so that's cool. Now, if you're doing the same thing with elliptic curves, then things get a little bit more iffy. If you were here, by now it's 5 years ago at 31C3, then I were giving a talk about elliptic curves, and we've been ranting a little bit about Weierstrass curves. And one of the things that makes Weierstrass curves nasty to implement is that you always have to talk about this extra point. So you have a nice curve, and then there's an extra point called the point at infinity. And this point of infinity messes up most of our arithmetic. So we don't have nice formulas where you just say, hey, well, this is our neutral element, and so we start at this, and then we keep on doubling this. Most of the formulas have this exact point as an exception. So we can't initialize there. There are ways around it, but the default is not as easy. There are some nicer curves. We've been advertising Edwards curves and Montgomery curves. So on Edwards curves, the neutral element is nice. This was the starfish shape, and you have this point at 12 o'clock, and you can just do it. So for Edwards curves, everything is nice. And I should also do a shout out to Montgomery curves. For instance, the famous curve 2519, which you might have in your browser or in a cell phone, that is using formulas due to Peter Montgomery, which are very happy about this data flow, and you even getting a discount. So you're doing basically one doubling and one addition for each bit. Same as a squaring multiplication, just it's called addition here, so it's like, okay, then would comment that probably this is just to make sure that we mathematicians keep lifetime employment, because nobody could possibly understand it otherwise. So it's all the same. It's called addition, doubling. Sorry for that, not my fault. Came before me. But you're getting this combo of addition and the doubling for less than it would take otherwise. So it's not as bad as it looks like for RSA or for Diffie-Hellman. In fact, the reason that 2519 gets used with these Montgomery formulas is that for that bit size, it's the fastest way you can implement scalar multiplication. So it has a nice feature of being constant time and is cheaper. If you needed some more motivation for wanting constant time, there is an additional benefit of constant time, namely you have figured out how long something should take, and so certain things should not happen. So if you know that your arithmetic does finish in time x, you will not enter an infinite loop, as the Microsoft cryptography library did recently for Windows 10.
Oops. Yeah, constructive talk, you said. So now we've had bug, and a little bit of fixing. And maybe you believe that, yeah, okay, these timing attacks are a problem. And sometimes people do believe, like OpenSSL, they've got a few subroutines which are labeled, claimed to be constant time. And there's some other crypto libraries which say, yeah, we've got some constant time code. It's not pervasive by any means, but some people say they're trying to do things in constant time and avoid these attacks. And then, well, is that true? I mean, people make claims about crypto all the time, like RC4, which was used until pretty recently. Sorry?
That's bad crypto.
It is bad crypto, but it was introduced with a claim that it's great crypto. RC4 is the crypto you want to use. And somebody gives you RC4 software. Well, originally it was proprietary, but eventually it was leaked, and then everybody had RC4 software. And this software, yeah, it's a strong cipher, and it's constant time. And, well, how do we check these things? Well, the strength of the cipher, that's outside the scope of this talk. It's not a good cipher. Yeah, don't use RC4. But how about the constant time property of RC4 or something else? Well, this example actually uses RC4. This code is maybe a little bit weird. So let me first look at what this code does and then say what Valgrind is doing with it. This code is sort of the start of code to encrypt using RC4. And what it does, you see there's some key running around. There's some space allocated for the key, 32 bytes. Maybe you want to use a different length. You can try this for different lengths of key, but 32 is a reasonable length of keys. And then, okay, the key is allocated. The program will abort if the malloc failed, and then at the end, it frees up the key properly. It doesn't ever initialize the key. So this is maybe a work-in-progress program, but okay, there's some space for a key. And then it expands the key. RC4, there's a key expansion process into what OpenSSL calls this RC4 key structure. And then, oh, there's supposed to be some encryption after this. Well, that didn't quite happen yet either. But this program is still something you can compile. And the compiler, with normal optimization options and without linked optimization and so on, it won't realize that this program is doing nothing. I mean, maybe the RC4 set key is, I don't know, crashing your system or producing some output or something. So the compiler will call malloc and RC4 set key. And then you can try running this program under Valgrind. Now, I'm sure lots of people here have used Valgrind or Address Sanitizer for checking for memory problems. Valgrind has the advantage that it works on binaries. And maybe some people were in room C for the previous talk about fuzzing, and it's really helpful to have tools that work on binaries. So you don't have to worry about getting into the whole software engineering process, compilation process. You just take the code that you're going to run, like the RC4 set key from OpenSSL. You don't have to recompile or redo anything with OpenSSL. You can just run Valgrind on your compiled code, and it will run this program and allocate space for a key, and then it'll call the RC4 set key and run through. Valgrind interprets every machine instruction. And while it's doing that, it keeps track of, all right, which memory is actually memory that's, you're allowed to talk to. For instance, the malloc is setting aside this amount of space on the heap, and then, well, you're not supposed to be going before or after that, and Valgrind is trying to keep track of what your pointers are pointing to, and then when you read and write data, then it's going to say, oh, you're not allowed to do that. And one of the things that it checks is, suppose that you have some uninitialized data, and you use that as a pointer, or you use that as a branch condition, and you try to do an if or an x bracket I where I is not initialized, then Valgrind will give you an error. And that actually happens in this code. The malloc array, well, that's uninitialized. And then Valgrind will track all of the uninitialized data, like taint tracking. It'll figure out all of the other computations on uninitialized data inside RC4 set key, and then it will complain. So you get an error message, looks like this, usual kind of Valgrind error for the people who've used this tool, and then it'll say there's some use of uninitialized value, which is not just any use. This means that you've been doing some array access, x bracket I, where I is uninitialized. And that's where Valgrind, what would it mean? It makes sense that Valgrind would say, oh, I don't want to continue past that x bracket I and just guess. It's trying to figure out if you're accessing some wrong spot in memory, and if I is uninitialized, it just says that's an error. You're not supposed to be doing that. And similarly, if you do an if based on if I, where I is uninitialized, then Valgrind will say, no, you're not allowed to do that. And it'll produce, well, not exactly the same error, but something else, another complaint about a branch based on uninitialized data. And hey, that's exactly what we want to do to check whether this RC4 set key is constant time code. This is checking, is any of the key information, is that being used for a branch? Anything derived from the key, is that being used for a branch, or is it being used for x bracket I, which could be getting into one of those cache timing attacks? And so if Valgrind says there's a problem, then you investigate and you fix it by throwing away RC4, or whatever you have to do to fix your software. And if Valgrind says there's no problem, then hey, cool, all done.
All right, so it is a happy talk after all. So we're in a happy situation that we have constant time exponentiation or scalar multiplication, we have constant time RC4, under a few of the conditions. So one of the things is that your arithmetic, in the end you have to implement your computations on the elliptic curve, or you have to implement your arithmetic modulo RSA modulus, and you have to do this long integer arithmetic in constant time. But you can again check this as well.
Valgrind will, every single machine instruction, it's going to follow through, so Valgrind, awesome tool.
Well, there's another condition that the processor doesn't screw you over. The processor tells you, well, okay, I'm going to do a multiplication, I'm going to do division, I'm going to do an addition. Now, if you have something where the processor is going to say, I do this in one single clock cycle, then that's probably okay. So you check the manual, you check the reference code, and the reference manual, and you look at how long it takes for one multiplication, for one addition. You look at like when you have access to it and so on. So that's fine. But how about other processes? So I had a poor student look at the Cortex-M3, so that's a low-end ARM processor, and we asked him to do some nice implementation of elliptic curve cryptography. And if you're having a multiplication which is taking two 32-bit words and producing a 64-bit output, so twice as long as multiplication should be doing, and then you look at the cycles count, then you're seeing 3 to 7 cycles footnote C. Footnote C tells you that this might be terminating early, depending on the size of the source value. There's a worst case latency of 1 cycle, something more, and up to 7 cycles. So, all right, so student with lots of time, it's only 2 times 32 bits inputs, right? You can you can't test all of them, but you can have a student test a whole bunch. And so he came up with this flowchart. So this Cortex-M3 gives you values between 3 and 7 cycles. It gives you actually every number between 3 and 7 cycles except for 4, depending on which of those branches you are taking, whether something is a special operand, yes or no, and whether both are special and one is 0. In that situation, Valgrind won't help you. In that situation, it's basically buy a different processor.
Yeah, this is what happens when we decide to do a constructive talk. 80% positive, this is going to be defense, yeah, and then we talk about it and realize, yeah, it's all broken. It's kind of sad. It's actually even worse. I mean, it's not just that the tools don't do what we want them to do for checking for things being constant time, but they also don't check that the code is correct. I mean, we spent half the talk now talking about timing attacks, and there's all these vulnerabilities to timing attacks appearing in the news, and lots more that don't appear in the news. And then suddenly there's more CVEs, which are not just timing is going wrong. This is like, okay, let me explain this. First of all, crypto memcomp. This is a function inside OpenSSL, which says it would be really embarrassing if OpenSSL had that 1 byte at a time password checking or authenticator checking inside the code. So crypto memcomp has been there forever in OpenSSL, and that is doing, supposedly, constant time comparison of 2 byte strings. Now, it's not that OpenSSL does everything in constant time, but it does this in constant time. And the PA-RISC implementation, because of an implementation bug, the PA-RISC crypto memcomp function only compares the least significant bit of each byte. Now, this is from May 2016. Somebody thought that they knew what PA-RISC processors are, and it's a good idea for OpenSSL to have assembly code for comparison of 2 byte arrays on the PA-RISC. I don't know how many people actually have ever used a PA-RISC processor. Can I see? Oh, okay, I see at least 10 hands being raised. I'm impressed. This is not the world's most popular processor, but it exists, and you can write assembly code for it, and maybe you can even find some machines where you can run this code. And actually, it's not crazy that OpenSSL is doing assembly code for things, because compilers screw things up pretty frequently. On the other hand, as this particular implementation illustrates, humans also screw things up pretty frequently. So what does this bug do? What is the impact? Well, let's look at the advisory. It says, this allows an attacker to forge messages that would be considered as authenticated in an amount of tries lower than guaranteed by the security claims of the scheme. Okay, let's figure out what this means. So you've got a message, and it's got typically a 16-byte, 128-bit authenticator at the end of the message. And then this crypto memcomp is being used to check. It recomputes the authenticator with whatever mathematical function, and then checks, is the result equal with crypto memcomp to what's coming in from the network. And if somebody's modified the message, then hopefully they can't compute that same 128-bit result. And now we try with this PA-RISC crypto memcomp on your PA-RISC server, we try comparing the authenticator that's computed, 128 bits, to the 128-bit correct authenticator. And it's only comparing the bottom bit of each of the 16 bytes. So it compares 16 bits, which means that instead of a 2 to the minus 128 chance of forgery, it's a 2 to the minus 16 chance of forgery. So the attacker just tries 2 to the 16 messages, and one of the forgeries is going to work.
It's lower.
Sorry?
It's lower.
It is lower, yes. 2 to the 16 is a lower security level than 2 to the 128. This is like classic British understatement of your security level is perhaps not quite what you wanted. Okay, PA-RISC, let's forget about PA-RISC, just like the whole computer industry has, and focus on Intel. Now, okay, I mean, PA-RISC, it was a nice idea at the time. Sun used to have these SPARC processors. Now Fujitsu still makes SPARC processors. I don't think anybody's trying to preserve PA-RISC, but people have these ideas of making new instruction sets, and, at some point, Intel made a new instruction set, and it got really popular, and they kept extending it and kept selling nice, fast processors. So here's, using AVX2, that's this 256-bit vector instruction set on current Intel and AMD processors. There's an implementation of 1024-bit modular exponentiation in OpenSSL. And the code from July 2013 was discovered in 2017, or announced in CVE 2017-3738, to have an overflow bug. Now, what's the consequences of this bug? Let me guess, it's a lower security level? Well, they say attacks against DH1024 are considered just feasible. Now, yeah, you shouldn't be using DH1024 in the first place, but if you are, then if the attacks are getting just feasible, does that mean 2 to the 16 computations? Does it mean a day on your laptop? Does it mean a year on a cluster? I want to know how hard the attack is. And, well, this isn't really answered. And there's more that's not really answered in the advisory, because they say, well, you're probably not using DH1024, but maybe back when this was announced, you were still using RSA 1024, or maybe DSA 1024, and those would also use the same subroutine. And then the advisory said that the attacks against RSA 1024 as a result of this bug would be very difficult to perform and are not believed likely. Now, what's happened here? There's the original crypto system, and then there's a bug which basically makes a new crypto system doing a wrong computation. And I mean, this notion of wrong, well, it's a different crypto system. And then is that new crypto system, this slightly different RSA 1024, you shouldn't criticize it, it's just, differently abled RSA 1024, and it's maybe it's secure, and they say it's going to be fine, and well, has anybody really looked at this? Normally, if we have a new crypto system, then we want it to go through a whole lot of review, because there's lots of things you can do wrong. And it's really important to get these things right. Lots of people were using RSA 1024. You shouldn't, of course. You should use something much bigger or switch over to elliptic curves. But if people were using RSA 1024 and they had these wrong computations happening, what are the consequences? Where's the papers analyzing this widely deployed crypto system? It's like saying, yeah, we've deployed this crypto system and we've looked at it ourselves and we've decided attacks aren't likely and just believe us. Well, people say this sort of thing.
If you can't break it, it's going to be fine.
Yeah, okay, yeah, you're right. Everything's fine. And similarly, a few weeks ago when OpenSSL put out another advisory for another bug like this, CVE 2019-1551, it's not that we knew this was coming and we figured we would have a talk about bugs in crypto software just to make fun of this. I mean, these things happen so often. There's so many of these bugs, and we don't know what the consequences of all these bugs are. They just keep happening. Here's an example of just one piece of the patch for the 2017 bug. Yeah, the code before already has...
That's correct.
Oh, you're right. The patch adds some lines saying correct. Oh, well, okay, that's clear enough. Next slide. How about post-quantum crypto? You got these top hundreds of cryptographers around the world fighting against the threat of quantum computers and putting together the next generation of cryptographic software protected against quantum threats. That's going to be carefully evaluated, right? Everything's going to be just fine. Well, no. Falcon, for example, this is one of the round 2 signature competitors in the NIST post-quantum cryptography competition. Well, post-quantum cryptography standardization project. And this one, there was an announcement in September 2019, which said, here's a quote from the author of the software, saying, well, there's some bugs, and the consequences are the signatures leak information on the private key. And they also make the software sound faster than correct software would have been. And interestingly, all of the implementations, all of the latest Falcon round 2 implementations that were released had the same bug. They all had the same test vectors. They all were, you could cross-check them, and they were doing the same leaking, different cryptographic computation, which presumably has lower security, and then are we going to spend a lot of time figuring out how low the security level is? The author also commented, the fact that these bugs existed shows that the traditional development methodology, being super careful, has failed.
All right, so what can we take from here? So mathematical complications in cryptography is thinking of like elliptic curves, what I mentioned. If you have these special points that need extra treatments, you have to watch out, are you even allowed to add those? Can you even represent this in your software? Those do make your software more complex. Something that we saw in the Falcon implementation, it was a new system and it hasn't been studied for long. So something which has been studied for a long time, like RSA and ECC, we still see issues with it. Things get worse if you have side-chain countermeasures. So as one example, you saw how I was trying to avoid the leaking that whether the bit is 1 or 0 by introducing arithmetic. Now, if you have to review that code before, where it just says, if the bit is 1, do this, if the bit is 0, don't do anything, versus the code which has the arithmetic instruction, it's more complicated. So side-chain countermeasures also add more complexity. Or Dan was mentioning this comparison bug in the PA risks. This was also because people were trying to make the comparison not leak information through timing, so they made a new implementation and introduced new bugs. And then, of course, with post-quantum cryptography, we're getting a whole bunch of systems like Falcon, which have been less studied, where we have less experience in how to implement it secure. We don't even know all the pitfalls that add to the complexity where we have to watch out. So it is a problem to review cryptography. Another problem with crypto is that we have this drive for speed. Crypto runs through large volumes of data, so we have to be really careful. We have very small code. We have to run it many, many, many times, and we will optimize the hell out of this. Doing like one squaring for each step and one multiplication for each step really is annoying, so we're trying to squeeze it here, we squeeze it there. So that makes it more error prone as well. And also, you're getting a huge amplification of implementations. You will have implementation for your x86 architecture. You're going to see some with AVX2 instructions, some without AVX2 instructions. Well, you might go all the way down to PA RISC special instructions. So there is, for each CPU, there is the dedicated implementation, not just the reference code. And then, if you look at, for instance, Keccak, which was the winner of the SHA-3 competition, so it's a relatively new hash function which only exists for like new platforms, but still they're having more than 20 implementations for different platforms in their library. Or Google, in order to get speed for hard disk encryption on some lower-end smartphones. So if you have a cheap smartphone, it might have just in Codex A7 rather than the new architectures which have AES support. And so they were like, okay, well, maybe we should add full disk encryption, but what we have sitting around is just too slow. Doing AES without the hardware support would drain too much battery. And so they went even down the road of taking a cipher specified by the NSA, the spec cipher, and they put it on there because it seemed to be the only thing that was satisfying the speed requirements. Now, they did switch after some public outcry, in particular, Jason Donenfeld did a lot of work there to make them switch to something better, and they then did another implementation, so yet another code base, to having a recently designed combination, which they call Adiantum with XChacha. So there is a lot of code to review and a lot of places to get errors. So how do we deal with this?
Well, maybe if the problem is all these complicated implementations of all this complicated math, maybe math is the solution. So here's...
That seems to help.
Sorry?
That seems to help.
Yeah, more math.
1 + 1 is 2.
So that's a comment from the bottom here from this book from 1910. From this proposition, which is proven in very comprehensible language here, it will follow, after we've defined addition, that 1 + 1 = 2. And this is on page 379 of this book called Principia Mathematica, Principles of Mathematics, by
When
Whitehead
do they
and
get to
Russell.
3?
I don't know if they do 1 + 2 = 3. That sounds more complicated. But somehow they find it important to prove something, and like in all this incredible detail, it's some sort of like machine language for proofs, and then people complain that their machine language has bugs. And well, people have worked on this over the last more than 100 years, and they would actually recommend, there's fans of this who say that, yeah, you should be going through this kind of pain. You should spend 379 pages proving that your code works. So you should take your software and you should write down a formal proof in incredible detail, not just to convince yourself and some friends, but you should convince a computer that's doing automated checking of your proofs. And that computer program says, yes, you have a correct proof that your software is computing the right thing. And what is the right thing? Well, you have to carefully define that, specify your language for your software, specify what the input-output relationship is supposed to be, and then prove that you have that input-output relationship for that software. Assuming, of course, that you've gotten all that right, then your proof, if it's checked, then yeah, everything should be fine. These tools, they work, but there's something, just to give some context, there's something that mathematicians who do proofs all the time don't like these tools. Occasionally they'll use them, but it's really not a popular set of tools because they're such a pain to use. Nevertheless, they have enough fans that some amazing results have happened. So Evercrypt, this is something, there's like 15 authors on the paper, and they have a crypto library which has implementations of all the crypto you need, as long as you don't care about any of those NIST curves or post-quantum crypto or, well, here's the list of what they do support. It's got some public key stuff and some signatures, some symmetric functions. It's got arguably enough to do, like HTTPS you can do with these primitives. And that's what Evercrypt supports. In the case of AES, you need your CPU to have AES instructions, so maybe that's not so portable. But okay, it does support some other ciphers on any platforms, and you can use this, and there's proofs. People have actually done, the Evercrypt paper is reporting how they took some standard proof tools and actually formally went through this software does exactly the right calculation, which is like, okay, that's some serious guarantee. The good thing about this is that the code really has the maximum assurance of any code that we've seen for cryptography. That it's really saying, yes, this code is computing the right thing. If you use Evercrypt, then it will compute the right output for every input, exactly what is specified. Assuming the specification is correct, assuming the processor is correct, assuming the compiler is correct, because a lot of it's written in C, you need your C compiler to be correct. But, well, okay, you can deal with those problems separately. How do you verify CPUs? How do you verify compilers, et cetera, and have people review the cryptographic specification. So it's feeling like something serious is being accomplished here. The only problem is that it's such a pain to do. For every implementation, you have to do quite a bit more work. And people are getting lots of practice building better tools, but it's still a ton of work to do these formally verified pieces of cryptographic software. An example of how hard it is just illustrated by that list of what Evercrypt supports. They've got some implementations of these functions. They even have, for Intel chips, some fast implementations of some of the functions. But if you want something that's fast on your smartphone or smartwatch, where maybe performance is more of an issue than on your, say, big laptop, then no, Evercrypt doesn't give you fast implementations. It does have something that works, but it's going to be several times slower and nowhere near what Tanya was mentioning about trying to squeeze out all the last speed. It's really far behind the state of the art in speed because it takes a lot of human time to take a new implementation and prove something about it. So what do you do when you don't have proofs? Well, of course, you test stuff. Now, we could spend the whole hour about like how cool testing is. And just, let me actually see a show of hands here. How many people here have ever had this feeling of, oh, I wish I had done some more tests of this code, like this bug that I had. Let me see a show of hands. I see pretty much everybody in the audience raising their hands. Okay, now, how many people have ever had this feeling of, oh, I did too many tests? I see, okay, maybe about 20 people out there have this feeling out of about, 1,000 something.
Replications?
Sorry?
Who's in both camps?
People who thought they tested too much and too little? Yeah. Of course, testing is fantastic. You should test everything, and if you find that testing is something hard to do, then it's probably because you screwed up in your factoring of the software that you're trying to test. You have too much cohesion. You should be modularizing it more and have a piece that you can test. If you do test-driven development, then you will basically have working code all the time. And that's a really nice feeling, except, well, there's a little problem, which I'll get to. But something like the crypto memcomp bug, for example, in OpenSSL for PA RISC, where it was only testing like the bottom bit and seeing do the bottom bits match. That's something which gives the wrong results for 1 out of 2 to the 16 inputs. Just random inputs will give the wrong results. So if they try 2 to the 16 or try millions, billions of tests, it doesn't take that long. And then it's going to catch that. Or instead of trying just totally random tests, the whole fuzzing philosophy says, let's try to smartly choose what you're going to test. And you try, for instance, you try a string and then try flipping a few bits here and there. Does it give the right result of a comparison? And that very quickly finds that the crypto memcomp doesn't work. And these are not just things that you could think of doing retroactively. This was actually implemented in the SuperCop crypto test framework, before the bug was introduced in OpenSSL. And it's just, well, the crypto code wasn't plugged into that framework, so, well, we didn't catch the bug. But it's like we almost could have if there had been a bit better organization of the testing effort. In general, if you see a bug, then at least retroactively, you should find yourself thinking, all right, how can I make tests that will catch that bug? And usually there's a pretty easy answer to that. And then you add that to your regression test suite and make sure it never happens again. And then if these regression test suites are shared enough, then it never happens to anybody again. And that's really effective. Except, well, the main thing that goes wrong with testing is that you're not testing all of the possible inputs. And so we've seen time and time again millions of security holes, which are the attacker is finding some input which nobody thought of testing for. It wasn't part of your random testing. It wasn't even caught by fuzzing. It's just some obscure kind of input where the attacker says, haha, if I try an input of exactly that length after setting up the following condition, then the following weird thing is going to happen, and then I can take advantage of it like this. There's some input that behaves in the wrong way, which you're never going to find through testing or even with the most advanced fuzzing that we have. So how do you deal with this? Well, that's not so easy, and it's something which definitely affects crypto. For instance, November 2019, Nathan Sarkar said, the fastest code for one of the standard elliptic curves out there, curve 448, high security, modern elliptic curve crypto. This is bigger than 25519 if you want something at a higher security level. There's a bug that randomly happens with probability 1 in 2 to the 64. Well,
that's a lot of tests.
Yeah, I'm not going to do 2 to the 64 tests. I mean, we've done some computations at that scale, but it takes a lot of effort to set that up, and it's not something you do with lots of different pieces of software again and again. Could an attacker find those inputs? Well, it's clear in the paper announcing this, Nathan Sarkar say, all right, here's some inputs which make this operation fail inside like a subroutine. Doesn't mean the attacker can find inputs to the whole crypto operation that make it fail. Should there be more analysis of like how devastating this bug is, or should we just get rid of the bug in the first place? They say, all right, certain kinds of inputs, the code gives wrong results, but it's very low probability, so known answer tests are not going to find this. And so they say you have to prove correctness. And this is the dichotomy that people often say. You have to either, well, do some tests that'll find the common bugs, or do proofs. That's a lot more work, really painful, but that'll find all of the bugs. There's another approach, which is symbolic testing. And this is something where I'll take memory comparison example, not for PA risk, but on the left side here, let's not think about this as testing, but code auditing. On the left side here is crypto memcomp for normal Intel chips, x86-64, inside OpenSSL. And you can read through that, well, maybe you can't because the font size is too small, but you read through, or maybe you're not fluent in assembly, but you read through, and eventually you say, here is the computation that it's doing for some particular size of input. Let's take, for example, 3-byte inputs. Of course, you have to try every length that you care about, like 16 bytes is very common. So for each length, you figure out what does this code do. And for instance, for 3-byte inputs, it's taking x0, x1, x2, comparing to y0, y1, y2, and then, well, how is it doing that comparison in constant time? Well, it's exclusive ORing x0 and y0 together, exclusive ORing x1 and y1 together, exclusive ORing x2 and y2 together. So now it has 3-byte XORs. It ORs them together bitwise. So that's a number between 0 and 255, where if the arrays matched, you would get 0, 0, 0, and then everything else is going to be 0. If there's any difference, then the XORs will be between 1 and 255, and the OR, the bitwise OR, will also be between 1 and 255. And then you convert that to a 64-bit integer, put 56 extra zeros on it, negate that integer, shift right, and if you think about this for a moment, you see that you always get 1 if there's any differences in the inputs. And that's a logic you can go through as a code reviewer to say, yes, this does work correctly. You start from the assembly, you figure out what it means for each size that you care about. That's this graph, this computation graph showing the arithmetic from these inputs to DAG, a directed acyclic graph that shows how the inputs give you some output through a series of computations. And then, well, you analyze this graph and say, yes, this works correctly, and do it again for each length. All right, there's tools which make this really, really easy to do. Let me highlight Anger. It's not the only tool out there, but it has the big advantage of working on binaries. It starts from Valgrind, from libvex inside Valgrind, and then builds a lot of extra cool stuff on top of that. What Anger does is that whole red arrow inside the previous slide, it does that for you automatically. It will take your binary and it will run through the instructions and tell you, all right, here's what that did for your input arrays X and Y, and here's how the output is a graph from those inputs. Now this makes your code review easy because you don't have to think about memory access, pointers, you don't have to deal with the complications of the assembly instruction set. The output of Anger is a much simpler instruction set. There's no jumps, it's just completely unrolled, this DAG that you get as output. There is a constraint, which is that Anger, if it reaches a branch based on one of the inputs, X and Y, then it's going to say, ooh, there's two possibilities. Maybe you take the branch or maybe you don't. And if you do an array access based on any of those variable inputs, it'll similarly split that and say, well, there's all these possibilities for which array index you're accessing. But hey, we were getting rid of that. That was the first part of the talk, is we don't want to be doing these variable time instructions. We're just going to have straight line computations. Maybe you have some loops, but it's based on public data, not based on the secrets that you're trying to work with. So we get rid of this blow up in crypto code anyway. We want to do that to protect against timing attacks. And then that means that Anger runs really fast, and it gives you the unrolled code. And then it can even sometimes check the correctness of that code for you. So for instance, this crypto memcomp for 3-byte inputs, it will tell you, yes, this works. Now we have only 9 minutes left, so maybe I'll just very, very quickly show you what some code looks like, but I'll skip a bunch of details. This is a simple call to crypto memcomp on some arrays of size n. You define n to be 3 or 16 or whichever length you care about. Do this again and again. And this takes X and Y, those arrays, compares them, puts the result into Z. The compiler won't get rid of this code with normal optimizations because who knows what happens after main. Maybe the exit is going to look at the Z value because it's a global variable, and maybe it's going to do something with it. So this crypto memcomp will be called. And then Anger, well, okay, there's some setup of grabbing the binary, telling Anger that the memory is all filled with zeros to begin with. You tell Anger, all right, you're going to run the code in Anger, but instead of having zeros coming in for the X and Y, let's replace those spots in memory with some variables. Let's say that the X bracket 0 in memory, that's going to be the X0 variable, where we don't know what that is. It could be anything, 0 through 255. And same for X1, X2, and Y0, and so on. And then you run the program, and you extract some Z's out of all the possible universes you get at the end. And for each one, that all the magic is happening in the last lines here. After Anger's run through the code, you can just ask it, do any of the following classes of bugs, can they possibly happen? And then there's some automated tools called SMT solvers which can sometimes answer this question. They might run a very, very long time, but for this example, it runs in under a minute and tells you, yes, the code always works. All right, last slide here. What is missing? What are the people who are trying this approach working on? Well, you can always do, if you have constant time code, you can always do this Anger translation. Another tool which will do this for you, which I haven't used personally, but Manticore supposedly can do the same thing from binaries and comes with a lot of the same kinds of analyses. But I've worked with Anger, it works just fine. Also, it has this cool GUI called Anger Management. So Anger, yeah, it'll always convert your code into this DAG. And then the red arrow there, it'll always give you the results of that. And then all of the interesting problem at that point is if the SMT solvers aren't smart enough to see that the resulting code works, then you have to build some new tools, which will look at, for instance, you get one DAG for your reference code, which you've reviewed and you're sure it works. You have another DAG for your complicated, fancy vectorized assembly implementation. And then you want to see, are those doing the same computation? And you have to kind of match up those DAGs. And people will give these arguments that, yeah, this is why this is the same. And the whole game here is to build tools which are doing this. And this is, maybe I'll skip the sorting example aside from giving the URL. Just an example of doing this is for sorting code, where right now the fastest Intel chip sorting code for integer arrays in memory is some new sorting code, which is constant time. It's like 3 times faster than Intel's integrated performance primitives library, where they were trying to optimize sorting. And it is verified to produce the right results with some tools which look at the DAGs coming out of Anger and say, yes, that is a correct sorting program. If you're interested in doing this sort of thing, then you should say, all right, here's some crypto code where nobody's claimed that it's verified, which is most crypto code. You can just take random examples, and then say, all right, let's make it constant time first. If it's not, then forget it. It's going to be vulnerable to timing attacks, throw it away. But if it is constant time, then use Anger and get this DAG out of it. And then say, well, okay, why does that match some other code which is supposed to be doing the same computation, like assembly versus some reference C code, for example? And then figure out how you can match up those DAGs. And usually a little bit of Python scripting will do that matching for you. It'll tell you if there's any problems. Sometimes you have to get into the details of how the crypto computations are done, but it's actually fun. That's the great thing about this approach. Compared to all the proving tools, doing symbolic testing, symbolic execution with Anger, followed by matching up the DAGs, analyzing the DAGs, it's fun. It's actually a fun way to analyze crypto software. At this point, we'll be happy to take questions, so thank you for your attention.
Thank you. All right, we will do a very high-speed Q&A session. So please limit yourselves to questions, not comments. Microphone number 1, please.
Okay, I think it's a very short question. Is constant time really the only mitigation against timing attacks?
Well, it's a mandatory thing. I mean, you can do more, you can do randomization and such things, but you want to have that those don't depend on the secret data in a reproducible way.
All right, mic number 2, please.
Thanks for the talk. Can any approaches from real-time operating systems can be applied to cryptography?
So real-time is usually trying to say you want to make sure the operation finishes at most this amount of time. But the thing that happens in fancier timing attacks, like hyper-threading attacks, is that before you've even reached near the end of the computation, the attacker's already extracted the secret data. And so it's a different game that real-time operating systems are playing. If you have constant time code, that can be useful in the real-time context, but it's a stronger constraint.
Okay, thanks.
All right, back to 1, please.
Thanks for this amazing talk. I just had a question regarding Evercrypt. You said that the Curve 25519 implementation was slower than the other stuff that's available. From my knowledge, the Curve 25519 implementation Evercrypt is actually one of the fastest ones.
On Intel, yes. On ARM, it's slower. On Intel, it's at the state of the art. But on ARM, it's a few times slower.
Okay, thanks.
All right, internet, go.
Did the formal verification of Evercrypt also check for the lack of side channel attacks or just for the functional correctness?
It checked for functional correctness and a lack of timing attacks.
It's actually a constructive way of producing code which is constant time.
All right, mic number 7.
You mentioned compiler bugs. How probable would it be that a bug in Anger covers up a bug in your code?
It's possible, definitely. The whole situation for testing is that you've got your original code, maybe you made a mistake there, you've got your test framework, maybe you made a mistake there, and you're trying to have these be sort of independent tests. And then ultimately, of course, if everything's proven, then yeah, you can imagine proving that Anger works correctly, do that once, and then it works for everything. But since it includes some kind of complicated stuff and all of Python and SMT solvers and so on, it's going to be some time before we're at that point. So yes, there's definitely a possibility of bugs in Anger. It's something to worry about. As long as they're kind of independent of the bugs that you'll make in your crypto code, then you're reducing the risk of errors.
All right, Mike, the Signal Angel, please.
Is there progress in the formal proof of true randomness?
That's enough of an
Let's
answer, I
skip
think. Mic number 1, please.
What's the status of doing pairing-friendly, or arithmetic and pairing-friendly curves in constant time?
So this is, again, a little more complicated. So if you just want the scalar multiplication, the TPM fail paper was also attacking the BN curves. So just the same issue appeared there as well. So the implementation were not constant time, even though they were inside the TPM code, which should have been validated. The pairing on top of it is looking a little bit like exponentiation computation. So the same tricks will work. At this moment, the best vetted code apparently was not constant time.
All right, microphone number 1, last question.
What about superscalar processors? Do they mess up your carefully crafted constant time algorithms, or is that, at least from a certain distance, not relevant anymore? They are short.
The way to think about it is that you want to have that there's like some isolated data which is holding all your secrets, and then there's never anything which is copied out of that sort of safe environment into the metadata which is controlling timing. Now, if you have a superscalar processor, you've got multiple instructions happening in a cycle, but as long as the decision of which instructions are being executed is not based on the data that you're working with, then you're good. And that's where you have to be sure that the processor is handling each instruction, the time that it takes, is only based on the other metadata outside the secure environment.
Okay, thank you for this great talk, and please thank our speakers again.